Hello guys, my name is DC Chandra Reddy of Data Science C section. So my applied physics tech talk topic is quantum security for the physical layer. Let's dive into the topic. So introduction: the physical layer is the lowest layer in any communication protocol set, often abbreviated by as PHY. It represents the specifications for generating, modulating, and transmitting signals over a network. Next, securing the physical layer, however, is notably different from the other layers comprising the protocol stack. Higher protocol layers resort to security schemes that naturally lie within the cyber domain, such as encryption or digital signature, while similar capabilities for the physical domain have not yet been developed. This is due to fundamentally different type of security required for controlling access to a physical medium. Next, principle of quantum communication. Quantum communication is rooted in the field of quantum information, which also includes quantum computing, quantum cryptography, and quantum sensing. At the heart of the disciplines is the use of quantum mechanics as the underlying mathematical framework. This distinction has been shown to lead to several notable differences as compared to conventional information technologies based on classical mechanics. In this session, we offer a primer on the same of principle of quantum communication and especially those that may be used for securing the physical layer in a communication system. Communication, quantum communication, like classical communication, is built up from logical states, namely ones and zeros. These logical states are the information that must be encoded into a physical system and relayed according to same chosen protocol. Quantum optical communication. Realizing the novel aspects of quantum communication requires adopting and encoding in some selected quantum physical degree of freedom. As noted above, qubits store of a continually variable value that mimics an analog signal up to the time So, the realizing the novel aspects of quantum communication requires adopting and encoding in some selected quantum physical degree of freedom. As noted above, qubits store a continuously variable value that mimics an analog signal up to the time of measurement, at which point is converted into a digital domain. Modulation corresponds with preparation of physical modes in a desired sequence, just as is done with conventional communication. Difference arises is how measurements affect these modes and correlations that can persist between disparate signals. In this section, we describe some of the ways that optical technology can be used to realize quantum communication. Quantum seals. These are several notable uses for quantum communication. These include quantum key distribution (QKD) for establishing secure communications, quantum teleportation for busing information with a quantum computer, entanglement swapping for setting up long distance quantum networks. These are several notable uses for quantum communications. This includes quantum key distribution for establishing secure communications, quantum teleportation for using information with a quantum computer, entanglement swapping for getting the support distance quantum networks, and quantum seals for monitoring the integrity of physical boundaries. While this section focuses on the operation of quantum seals, many of the same principles of quantum communication and quantum optical encoding arise in the discussion of these other application domains. Seals are widely used for verifying the integrity of enclosed systems, including storage containers, physical perimeters, and fiber networks. Cyber physical system security. Conventional communication is a complex hierarchy of layers and protocols for synchronizing and share information. Securing each layer is an equally complex task with its own hierarchy of approaches. Among these, the physical layer stands out as a being immune to the information theoretic approaches that characterize, for example, cryptographic security at application session layers. This is because the type of assurances that must be provided are very different between the physical and non-physical layers. Whereas the non-physical layers attempt to prevent knowledge about the transmitted data. Securing the physical layer requires preventing access to the transmitting signals, preventing access to the fiber that conducts the communication signal is perhaps the most straightforward approach to securing the physical layer. So, summary outlook. There are several outstanding research and development issues that must be overcome before adoption of quantum physical layer security. In this session, we offer a primer on some of the principles of quantum communication and especially those that may be used for securing the physical layer in a communication system. Quantum communication, like classical communication, is built from logical states, normally ones and zeros. These logical states are the information that must be encoded into a physical system and related according to some chosen protocol. So, the quantum communications, like classical communication, is built up from logical states, and namely ones and zeros. These logical states are the information that must be encoded into a physical system and related according to the same chosen protocol. Realizing the novel aspects, the quantum communication requires adopting and encoding in some selected quantum physical degree of freedom. As noted above, qubits store a continuously variable value that mimics an analog signal up to the time of measurement, at which point is converted into a digital domain. Modulation corresponds with a preparation modulation of physical modes in a desired sequence, just as done with a conventional communication. Realizing the novel aspects of quantum communication requires adopting and encoding in some selected quantum physical degree of freedom. As noted above, qubits store a continuously variable value that mimics an analog signal up to the time of measurement, at which point is converted into digital domain. Modulation corresponds with preparation of the physical modes in a desired sequence, just as done with a conventional communication. Quantum optical communication. Differences arise in how measurements affect those modes and correlations that can persist between disparate signals. In this section, we describe some of the ways that optical technology can be used to realize quantum communication. Differences arise in and how many measurements affect these modes and the correlations that can persist between disparate signals. In this section, we describe out of the ways that optical technology and can be used to realize quantum communication. Differences. So, quantum seals. There are several notable uses for quantum communication. These include quantum key distribution (QKD) to establish secure communications, quantum teleportation for being used information with a quantum computer, enlargement swapping for setting up long distance quantum networks, and quantum seals for monitoring the integrity of physical boundaries. While this session focuses on the operation of quantum fields, many of the same principle of quantum communication and quantum optical encoding arise the discussion of these other application domains. Seals are widely used for verifying the integrity of enclosed systems, including storage containers, physical perimeters, and fiber networks. Cyber physical system security. Conventional communication is a complex hierarchy of protocols for synchronizing and sharing information. Securing each layer is an equally complex task with its own security of approaches. Summer outlooks. There are several outstanding research and development issues that must be overcome before adoption of quantum physical layer security. This includes standardization of how quantum information fits into a protocol suite and what is required for quantum physical sublayer implementation. There are several outstanding research and development issues that must be overcome before adoption of physical layer security. This includes standardization and how quantum information fits into a protocol suite and what is required by a quantum physical sublayer implementation. The emergence of cyber physical systems may offer a natural opportunity for resolving these integration issues and provide a convention path to introducing new concepts for the physical layer. The hardware required by a quantum physical sublayer is very similar to that called of existing and forthcoming QKD communication system. The emergence of cyber security physical systems may offer a natural opportunity for resolving these integration issues, provide a convention path to introducing new concepts for the physical layer. The hardware required by quantum physical sublayer is very similar to the called of existing and forthcoming QKD communication systems. So this is my tech talk topic of applied physics. Thank you.